so one more time. If we want to integrate a fraction, and how have you integrated fractions in the past?
Carefully.
Better than carefully, come on.
Break them up.
Well, you know we're going to break them up now, but why can't I do this as is? Yeah. Only thing we ever did was U sub it. We would U sub the bottom out, get cancel, end up with a natural log. That was our method of attack. This is definitely not trig substitution or something staring at here. So you can't do many fractions. So one of your methods of attack is to break it down into simpler, smaller fractions that maybe you do have the ability to integrate. And since we've learned how to do partial fractions, yes, you have to break it down into the partial fractions first and then integrate it after you've found the partial fractions. Good team! Trust me, it's going to look easier than what you've been doing, I swear. There's not a lot of problems on this test. So, the question is, do you remember how to do partial fractions?
There's something with a square. If it's a square, it's like
Okay. Well, first of all, you have to figure out what your denominators are going to be. So how do you figure out what denominators might have made this? Yes, you have to factor this first, which this is no big deal to factor. You have to factor it first to figure out what the denominators might have been. Which, this is a nice, normal, easy one. So, yes, our fractions had to have been x minus 2 and x minus 1. Now, you were starting to recall, how do you know what to put on top? Is it just an A? Is it an AX plus B? It's one power less than the power on the bottom. So if this is a first power, at most you can put on top is an A. And same way over here, the most we can have is a B. Okay, you now have to do the algebra to solve for A and B. So actually forget the integration sign for the moment. We're just trying to solve for A and B here. Total algebra. What do you always do when you want to solve equations that have fractions? Get rid of the fractions by multiplying by the common denominator. The common denominator is always, without fail, the original denominator. Do not use anything else. Actually, do not employ your own brain and try to figure out a common denominator. Use what is there. That's it, always. So, sorry, this is one of the rare times I'm going to tell you, don't overthink this. What is the original denominator? That's what you're multiplying by, guaranteed. So, I'm going to always on the original fraction, you're going to cancel the denominators, and you're just going to have the numerator left. All right, what's going to happen with the A and the B?
It's going to be x minus 1. The x minus
Yeah.
2 you cancel.
Yeah, because you're going to take it times x minus 2 and x minus 1. Well, x minus 2 is going to cancel, so you're going to be left with A and x minus 1, and yes, you can distribute that. And then, so what's going to be left with the B? Yeah, because the x minus 2 is going to be left, and I'm writing this out in an extra step just so I don't lose anybody, particularly for those who aren't with us today. So if I distribute that, I'm going to have ax minus a and bx minus 2b. Now, you are really close. You set the ones that have the same power of x equal, but you put the x's in there. No, you're just pulling the coefficients. You're saying, oh, if this is a 15x, then all the x terms on the right-hand side had to add up to 15. But don't keep the x. It'll just be 15 equals a plus b. There you go. So negative 14 equals negative a and a minus 2b. Because your goal here is you want to solve for a and b. Usually, by elimination, that's going to be... Oh my gosh, how easy is that? Woo, talk about nice. Yes, we already eliminate. We don't even have to make them eliminate. So I'm just adding down and going, gee, 1 equals, those cancel. 1 equals negative b. Woo, think you can handle this one? B equals negative 1. Okay, are you done? Which would be the smart one to plug in to find a? The first one, yeah. So if 15 equals a plus negative 1, I believe we know that a is 16. Now, the one thing I will not promise you here, we're advanced students, A's and B's will not always come out to nice little whole numbers. You will get fractions and icky little A and B answers, so don't flip if that happens. Whining will not help. So now, are you done? No, you aren't done. So now, you have to put it back in, the A and B back in, and now we actually have to try to integrate the crazy thing. That is good that it does not look as scary the first time. Okay. I am separating this out just so we can see. So since A was 16, I would actually recommend you write this as separate integrations. You have A is 16 over x minus 2, and then you've got a separate integration of negative 1 over x minus 1. Because they're going to integrate totally separate fashion. The first time I'm going to remind you how to do this the real, what now? Question, you look puzzled. A over x minus 2, so 16 over x minus 2.
I'm just falling asleep.
And then you got the.
And B is negative 1. I'm putting it back in these fractions.
Yeah, but then you got x minus 2.
So it was 16 over x minus 2 was the original. I got those from the factors, yeah.
Can't we just stop at the first?
No, we can't. That would be boring. You already know how to do that. You need to. This is going to be like the integrating the sine of 4x and getting a 1/4 cosine x minus 2. It's really 16 times the natural log of x minus 2, absolute value of x minus 2. Okay, so consequently, if it's just a simple little 1x, you know the derivative is just going to be a dx. So on this next one, can you tell me what it's going to become without having to do the whole u substitution? A negative 1 out front, natural log of x minus 1, of course, plus c. Now, the good news is the book is going to go, but hey, dudes, we know the properties of logs. We can simplify this answer and make it more condensed. Now, how did you know you're going to divide logs? It's a minus, yeah. In some respects, sometimes I think this looks nicer than what they're going to combine it into. Can you divide the logs, since you have them subtracted, with that 16 sitting in front? Nope. Where can I move it? I can't just get rid of it, but I can move it. Where would you like to move it to? A number in front of a log. It's the plug rule. So I can move that 16 up as the power. So I actually have then, let's not save, but we are saving. When we're done saving,
Save longer.
I can't. I don't think. Well, I don't know. Can I save it? Pause it for purpose. So I actually have then a natural log of, here's where I don't care. You can write this. It's still, technically, since it's a 16th power, 16, since it's an even power, is not going to guarantee it's positive. So they won't always keep an absolute value. They may just do a regular parenthesis on it to the 16th, because the 16 is going to guarantee it's positive. I am perfectly fine, and most people end up just leaving the absolute value on it. It doesn't hurt a thing. Over absolute value of x minus 1 plus c. Now, if you choose to moan and groan about these, I can arrange it that came out with a simple little nice little natural log integration. I could arrange it so that these came out to, some fun trig substitutions or something that you had to do to integrate it after you did the partial fraction. Yeah, I've always thought it would be fun to sit around and see if I could come up with a problem that had all the different forms of integration in it.
That's one problem.
Yeah, I know.
make it extra credit. You have to do extra credit for that.
Well, and I-
Yeah, and I don't really think I could pull it off. I don't think I could get them all in. But that's what. Because I made this monster horrible problem. Yes, that's the goal. All right, let's see here if we can. Oh, that's what I'm trying to tell myself. Oh, we got time. We got two. No excessively loud yawning. Yep, it is. Okay, my goal is we need to make it through this one and one more. If I'm going to show you the variety of wrinkles that can appear in these. Okay, this one. Why is this one different than the last one? You got a quantity squared. I did factored for you. That part's nice. But I'm out to see if you remember when you're setting up the partial fraction part, if you remember what to do with the quantity squared. Yes, it gets funky. Good way to put it. Okay, so we're going to have one with a 4x plus 1. The question is, what do I do with the 2x minus 3 quantity squared? Yes, you do make two of them. Do you remember what the two of them become? One of them is just stays 2x minus 3 squared. Yeah, the other one is just 2x minus 3, but why? That's the question. Because when you make the common denominator, you take the most that's in any one fraction. So since we had a square here, couldn't there also have been a fraction that had this quantity to the first power? Because that would be in this 2x minus 3 quantity squared. That would be part of the common denominator. It's just like if you have x squared on the bottom of your fraction, you have to have one fraction with an x and one fraction with an x squared, because x would be an x squared. It's part of the common denominator. Now, chances are good. 2x minus 3 may cancel, so it's possible. The one that's squared will never cancel because you wouldn't have had it in your common denominator without it. But the one to the first power may turn out the stuff on top zeroes out and that fraction didn't exist. But we aren't going to know that. So now, what goes on top of the first one? Oh, thank you. Well, we'll do the top, then we'll stop. NA. Does the square matter or not? It's what's on the inside, not the quantity. So it's just a B and a C. All right, we will stop it there and then start another part.